Welcome back, everybody, to our final online lecture. We hope this will be not the last our lecture, that Fraser will come at autumn to us. And I think it will be more interesting for students to see how Fraser looks like. So, Fraser, please start.
Thank you very much. It's been good to meet with you, and I hope I will be able to meet with you in person at some point before too long, if the situation in the world permits. So what I want to spend this week doing is just thinking about a few more topics in Poisson approximation. So what did we see last time? So last time we started off talking a little bit about Poisson approximation. We looked at some coupling ideas that were not related to Stein's method, just to sort of illustrate the kind of results that we can get using some other techniques, and illustrate some of the improvements that we can get with some in some different settings too. So, as with all things Stein related, we started our discussion of Stein's method for Poisson approximation with this characterization. So this is very closely related to the definition of size biasing that we had a couple of weeks ago, 3 weeks ago. I don't remember exactly when we did this now, but I think towards the beginning of the second lecture maybe. So we talked about this size bias coupling. So we had the way that we defined this when we saw this first in a Gaussian context, because it's possible to derive some Gaussian approximation results using the size bias coupling. But we defined this sort of size bias version by saying that, okay, so my x star was a size bias version of x, and we defined this coupling by saying that expected value of g of my size bias version is just the same as the expected value of xg of x divided by the expectation of x for all functions g for which those expectations exist. Let's not get too hung up on which functions g, and particularly in the continuous case that we were thinking about, because I don't want to think about this in the continuous case anymore. We're for the purposes of today, all the random variables we're going to write down more or less will be integer valued, so non-negative integer valued random variables, so in which case having g bounded or something like this is enough for this kind of definition. We need that, just as a sanity check, we want this mean to be, first of all, not zero. So usually almost everywhere I'm going to assume this mean, which we'll usually write down as lambda, is not zero, but if I forget to say that explicitly, then I'm certainly assuming it for everything that we're doing. So we saw this definition of the size bias distribution for any random variable x. So we applied it in the context of Gaussian approximation, but it arises much more naturally in Stein's method in the setting of Poisson approximation. This what we've got on one side of my characterization is exactly the sort of size biasing. And so this characterization of my Poisson is saying that I'm Poisson if and only if my size bias version, so this is just, if I move that lambda over to the other side of that equation, this is just the expected value of g of my size bias version, and this is the expected value of g of my shifted version. So that characterization we had for Poisson is saying that I'm Poisson if and only if size biasing is the same as shifting by 1. And more or less, I want to spend the vast majority of what we're going to do at the time that we've got today using this size biasing idea to give explicit Poisson approximation results. So the fact that we're...
Am I right that we used size biased for normal approximation, for Kolmogorov distance?
Yes, I think we did.
And here we use like like total variation distance for Poisson approximation that is in some sense closer, like Kolmogorov and total variations, in the sense of, I don't know, discrete and absolute continuous random variables.
Yeah. So in the setting where we're discrete, then you don't get all these problems with discontinuous functions and things, because you're not anywhere assuming any kind of continuity. So so somehow doing total variation, doing Kolmogorov distance are as easy as you want them to be. So you don't have these sort of difficulties with discontinuous indicator functions or whatever. Just arise. So yeah. So yeah. We can do Wasserstein approximation if we want to. There's very little that would have to change to be able to write down Wasserstein equivalents of the results. So yeah, so what I want to spend today thinking about is this sort of size biasing approach to Poisson approximation. So I guess the setup for that we saw last week. So we had the Stein equation that we wrote down, where one side is capturing the two terms in my characterization essentially, and the other side is a thing that I want to bound to be able to get a handle on how close some random variable w and this Poisson random variable z are. So I just replace all my j's by random variable w, take expectations, and I want to measure. I'm going to end up taking the supremum of the absolute value of what's on the left here to measure how close w and z are. I'll write that instead as a supremum of the absolute value of what's on the right. Again, partly because this is all I've now only got the single random variable w rather than w and a Poisson that I have to worry about. Now, the fact that we're thinking of a Poisson limit here is encoded in the form that I've got on the right-hand side, the particular functional form that I've got on the right-hand side of that equation. That's where all the Poissonness of the problem goes. Okay, so as we said, we'll think mostly about total variation distance, where we're just going to take these test functions h to be bounded, say bounded by 1, and we can bounded by whatever, we can always normalize it, but bounded by 1, let's say. We could do Wasserstein distance if we wanted to and take the class of Lipschitz functions instead. The only thing that would change are the bounds that I have on the solution to that Stein equation. So this, let me just go back up a second. So that's the equation we're solving. So I give you, as before, I give you an h, you give me back an f. So f is a solution to that equation. It's going to depend on h, and exactly what we assume about h will tell us how that solution behaves. So if I know that h is bounded, then I know that f is bounded by essentially 1 over root lambda, and the increments of f, so this delta is just right here, just in case so this delta f is just the difference between, well, it's just the increments of f, so f of j plus 1 minus f of j, delta f of j. So I can, if I know that h is bounded, f is bounded by essentially 1 over root lambda, the increments are bounded by more or less 1 over lambda. If I instead assume that my h's were Lipschitz, so all the same arguments that we'll use more or less everywhere in today's lecture will work. I just need slightly different bounds on my solution f to that Stein equation. I get a slightly worse rate in terms of lambda, in the sense that now f is bounded by a constant and the increments by 1 over root lambda. But they're the only things that will change, and I'm not really going to say very much more about Wasserstein things. So we saw last time we talked about how this sort of works in the independent case, because there's always the independent cases, and the easiest example to start with. We also saw how the arguments we had there generalized to a sort of local dependence setting, where I have some perhaps small class of random variables, and so that so I'm thinking about a sum of dependent Bernoulli random variables, and for each term in that sum we had some sort of small class of random variables which were strongly dependent on those, and in that setting we can use the same kind of arguments that we had before, but just we have to be a little bit more careful, but we can get an explicit bound which reduces to what we had before in the case where those x's were independent. So I'm not, unless anyone else had any questions about any of this stuff that we did last week, I'm not going to think about this sort of local dependence thing at all today. I want to take a different point of view, look at some different techniques for Poisson approximation. But if anyone did have any questions on that, then now would be a fantastic time to ask.
I don't know. I think everything is clear, but yeah.
If it is, then that's fine. But feel free to tell me if it's not.
As always, we have chat. Please ask the questions in chat, or you can orally ask them.
Yeah.
So, yeah.
So I guess the one thing I did want to say about this sort of leads into what I was going to say today. So, like we said last week, that this sort of all depends essentially on the covariance structure of my summands. These z's are just sums of various x's and whatever. So when I expand out these sums, I just need to know about lots of terms that look like expected value of xi times xj. So I need to know about the covariance structure between my x's. And if I wanted to, so what I want to think about today is using size bias techniques, and I can write down some very general results which use the size bias coupling and assume just a general sum of dependent Bernoulli random variables. And we'll sort of use this idea of size biasing to write down a very general upper bound on total variation distance in terms of the covariance structure of my summands. And I can do that, and there are results in the book by Barber, Holst, and Janssen, which is referenced in the notes somewhere, that will let me do that. But I'm not going to talk about that at all today. There are general results using size bias couplings that you can write down that require you to know, say that sort of the covariance structure within my summands, and I don't want to think about those because I want to think about a slightly different approach.
Which this is the same definition that we have already for size biased. Yep.
Yes.
Just
different. I'll say that in a second. Yeah. But yes.
Oh,
yeah. So this is just another way of writing down this definition. So if I take if I take this definition of size biasing that we had before, and just let G be an indicator that we're equal to some fixed number J, then exactly what I get there is exactly what we've got written down here. So that in a nice discrete setting where I can write down a mass function, then there are two equivalent definitions of size biasing. The sort of more general definition that also works, say, for absolutely continuous random variables, and this somewhat simpler definition to work with in the case where everything is where we can write down a mass function, and then it's sort of explicit why we're in some sense why we're calling this size biasing, because I'm just multiplying the probability of seeing a particular number J by J. I'm sort of biasing exactly by the size, and then the mean on the bottom, which again I'm assuming is positive, and I'll assume that's positive throughout the lecture, is just a normalization. So what we can do, I can write down much simpler upper bounds that don't need me to know all the covariance structure of my between all the terms in my sum. I can write down very simple upper bounds. Let me find one of them that we'll get to in a while. I will of course come back in a minute. So a very simple upper bound just depend on, let's say, the first two moments of my W. Okay, so W is a sum of let's think of it as a sum of dependent Bernoulli random variables. It doesn't actually have to be here, but that's usually the example we're going to think about. I can write down upper bounds which don't need me to know about the covariance between all the terms in that sum. I can get away with just knowing the first two moments of that sum. So a mean, which we'll call lambda, and the variance of the sum. So that's just the sum as a whole, that's not the individual terms. So I can write down very nice upper bounds, which are much simpler to compute in the sense that I don't need to think about the intricate detailed covariance structure. I just need to think about the variance. The price that pay for getting upper bounds like this is that these sorts of upper bounds hold under some particular monotonicity conditions. So under some particular conditions that we're assuming on the dependent structure within my sum. And that's what I want to think about today mostly. So at least for the next 40 minutes or so, is thinking about what these kind of monotonicity assumptions are, what they mean. I say that the reason that we want to make those kind of assumptions is because it makes my upper bound much easier to write down. Right? It's a much simpler upper bound conceptually and in terms of calculations, for examples. If I can get a kind of monotonicity to make these kind of things hold. So I guess the reasons that I want to think about this, I guess there are three reasons that I want to think about this in a Poisson setting. The first one is that I've done some work in this area, and I like it, and I think it's fun. So I think it's something I want to talk about, and I'm allowed to choose what I talk about. So that's a good enough reason. Secondly, it's something that doesn't or hasn't yet really been made to work in the same sort of generality, in the same sort of way for in say a Gaussian setting. Now there is some work in that direction as well. So this is sort of much more classical Poisson setting than it's sort of continuous setting. So I think it's worth thinking about while we're talking about Poisson things. And thirdly, it's genuinely useful in applications. So we'll see some fairly simple, fairly toy applications later on, but we'll see how these kind of monotonicity results actually happen in application. You know, actually, these monotonicity results can be applied in applications, and so we'll see that they genuinely are useful and they're worth thinking about. So one thing that we said that my Poisson characterization is saying that I'm Poisson if and only if my size biased version, my W star, is the same as the shifted version W plus 1. Okay. So that's the whole idea is that I'm Poisson if and only if those two things are the same in distribution. The sort of monotonicity that I want to assume now is some kind of stochastic dominance or stochastic ordering between those two transformations of W. Okay. So somehow if these two things were the same, I know that I'd be exactly Poisson. Somehow if there's some stochastic monotonicity between them, then everything becomes a lot easier. And it's not entirely clear so firstly, it's not entirely clear why that helps you, and hopefully we'll see that. But before we do that, almost the second thing I'll do now is to convince you that this sort of definition makes sense, because it's not clear that even if this sort of abstract condition is useful for making the upper bound simpler, is it useful in any way on getting a handle on real life dependent structures? But the first thing I need to do is tell you exactly what I mean by this. So let me just go back a little bit, and we'll start going slowly through stuff that will get us to where we want to be. Okay, so we'll get back to monotonicity conditions in a minute, but let me just sort of say, I guess, something else first. So as we said, it's clear that Stein's method for Poisson approximation can be thought of as a comparison between the shifted version of the random variable that I think is more or less Poisson versus its size-best version. And if I want to, I can make those sorts of comparisons explicit. So just use that representation, use the fact that I know that the increments of f are bounded in the same kind of way that we have before. I can explicitly write down a bound on what's going on here in terms of how far apart the shifted version and the size bias version of W are, in terms of the size of the increments of this solution F. Oh, we've got a lambda kicking around at the front there as well. Those increments were bounded by the minimum of 1 and 1 over lambda. The minimum of 1 and 1 over lambda. So I can immediately write down, if I want to, this sort of bound that makes explicit the fact that when I want to compare how far W is, when I want to bound how far W is from Poisson, then I can do that just in terms of how far apart the shifted version W plus 1 is from the size bias version W star. So this, as with other similar results that we saw in the, say, the exponential case a week or two ago, this is going to rely on having some explicit coupling between W plus 1 and W star. So we'll need some kind of explicit construction of that on the same probability space, and we can do that. We can write down general bounds that follow from this sort of thing. I say this isn't really what I want to do. What I want to do is think about exploiting monotonicity between W star and W plus 1. So there's a whole host of results we can get using this, but I don't want to think about this. What I want to do is think about monotonicity between those two random variables in terms of this stochastic ordering. So this turns out to be a fairly natural way to represent the kind of monotonicity conditions that we're interested in. So for those of you who may or may not have met this definition before, so for any two random variables, say x and y, I can say that x is stochastically smaller than y if the right tail probabilities for x are smaller than those for y for all possible tails that we might be looking at. Okay, so that's the definition that's sort of most useful in terms of the formulas that we'll write down. So it's just saying that wherever it is that I'm looking, the smaller random variable x puts less mass to the right than the bigger random variable y. So it's just a way that lets us essentially compare two random variables in a natural sort of way, and essentially in a way that's sort of making it clear in a very strong sense that x is smaller than y. So this is relatively strong. I mean, we're putting conditions on the whole distribution function of these two random variables, so it's a relatively strong ordering, but it turns out to be useful in this context. There are a couple of ways you can also think about this. You can equivalently think about this if it's sort of easier conceptually. First of all, I can replace these indicators of right tails by any increasing function. So x is smaller than y stochastically if the expectation of any increasing function of x is smaller than the same thing but for y. So this is this definition we started with is just the case where g is just a right-tailed indicator, but that's okay. Or equivalently, again illustrating just how sort of strong this assumption is, or ordering really is, saying that x is stochastically smaller than y is equivalent to saying that I can construct random variables with the same marginals as x and y in the same probability space, so which have the same inequality that holds almost surely. So I can construct these things on the same probability space so that the random variable that I've constructed that looks like x is almost surely smaller than the thing that looks like y. So it's however you sort of like to think about this definition, it's fine. I think that the easiest thing to think about is the definition we started with, where we're just thinking about the amount of mass that these two random variables have in the right tail. So, as we said, if I want to exploit some monotonicity here, a very natural way to do it is to think about stochastic ordering between this this shifted version W plus 1 and this size bias version W star. So let's start off by thinking about the setting where the size bias version is stochastically smaller than the shifted version. Okay, so that turns out to be a useful assumption, in that what it does is capture some ideas that are related to negative dependence. So by negative dependence, what do I mean? So typically we'll think about, typically I'll think about the case where W is a sum of dependent Bernoulli random variables. So this is, think of that as the sort of example, the sort of general example that we'll be working with. By negative dependence in this sort of setting, what I mean is that if I tell you that one of those x's is large, well, large in this case means 1, because all these x's are either 0 or 1. So if I tell you that one of these x's is large, in some sense that tells you that the others are smaller than you would expect them to be otherwise. Okay? So there are sort of a few ways that you can capture that kind of, that very imprecise intuitive idea, and we'll think about some of them, but say, so by negative dependence, what I mean is that if I tell you that one of the x's is large, then it tells you that the other ones are small in some sense. Okay. So one way that I can think about negative dependence, and I sort of don't want to dwell on this too much, this is just for those who sort of may have already met notions of log concavity and ultralog concavity of these sorts of random variables. So there's this notion of ultralog concavity, which Liggett introduces to capture ideas of negative dependence, which turns out to be equivalent, again, for those of you who are already familiar with these kind of ordering things, and if you're not, then don't worry. This definition of ultralog concavity is equivalent to likelihood ratio ordering between the size bias version and the shifted version, which is stronger than stochastic ordering. Okay? So if you're familiar with stochastic orderings and that sentence you understand what I'm saying, then that's great. If you're not, then don't worry, I'm not going to use likelihood ratio orderings again, and we're not going to use ultralog concavity again. But just to mention that ultralog concavity is a stronger condition than this stochastic monotonicity that we're going to be assuming. Okay, so, but what I really want to think about is a slightly different way of capturing negative dependence. What I want to focus on is a setting where these x's in my sum have this total negative dependence property, which says that for any increasing functions g1 and g2 that I want to look at, the covariance of this increasing function of one of my x's and a different increasing function of the sum of the rest of them is negative. So that's one way of capturing this idea that if I tell you that this thing xi is large, then the rest of them are smaller than I would think otherwise, because there's negative correlation, negative covariance between this xi and essentially the rest of them, at least the sum of the rest of them. Okay, so that's one precise way of capturing this idea that if one of my x's is large and the rest of them are sort of small, is that this covariance is going to be negative. This is one way of also getting a hold on a property that's called negative relation, which is and anything which has this total negative dependence property that we talked about also has this property of being negatively related, which I haven't written down the definition of just to avoid cluttering up more space. But what negative relation says is that if I it's just another way of capturing this idea that if one of my x's is large and the rest of them are small, because it just says that if I look at the expectation of an increasing function of all of my x's apart from 1, if I look at that expectation conditional on xi being 1, that's smaller than the unconditional expectation. I can write down the definition, but I'm not going to use it, so I perhaps won't. But it's just saying that if I condition on xi being 1, then the expected value of an increasing function of the rest of the x's is smaller than it would be otherwise. That's another reasonably natural way of capturing this idea of negative dependence. So what I want to do is convince you that, okay, so what I've told you about is this that I'm going to think about this stochastic monotonicity, the fact that my size bias version is smaller in the stochastic sense than my shifted version. I'm using that idea to capture negative dependence. So that is very much related to this somewhat more intuitive way of capturing negative dependence, this total negative dependence. I just want to convince you that if we satisfy this stochastic monotonicity, then we are that if we are totally negatively dependent, then we satisfy this monotonicity condition that we're talking about. So, in a sense, the results that I want to capture the results that I want to capture in this setting are include a class of totally negatively dependent sums. So, if I'm going to convince you of that, then what I want to do is I want to show you that that this size bias version is stochastically smaller than the shifted version when W is a sum of totally negatively dependent things. So I can capture that by saying that if I let G be an increasing function, what I want to show you is that the expected value of the size bias version of G is the expected value of G of the size bias version is smaller than the expected value of G of my shifted version. So that's what I want to show you. That's true if W is a sum of totally negatively dependent things. But I also know that this thing here is most easily thought about in this setting as using the definition that we already have. So this is just the expected value of W, G of W, divided by my mean. So let's think about what we've got here. Let's think about this expectation of W, G of W. So I can write this W as a sum of my x's, and I'll just pull that sum out of my expectation. Now, this G is an increasing function. All of my x's are either 0 or 1. So I can certainly get an inequality almost surely if I replace one of my x's in this sum by 1. So this Wi that I've got is just the sum of all of the rest of them apart from xi. So just the sum of all of the rest of my x's. Since xi is either 0 or 1, so it's at most 1, and G is an increasing function, so this inequality holds almost surely. So this W is bounded by Wi plus 1 almost surely, and so the expectations are bounded for increasing functions as well. The advantage of doing that is now I can use my use the fact that what I've got is an increasing function of xi there, multiplied by an increasing function of the rest of them, and use my total negative dependence definition, which says that the covariance between increasing functions of one of them and the sum of the rest of them is going to be negative. So if the covariance is negative, that means the expected value of the product is smaller than the product of the expected values. Okay, so that's just using my definition of total negative dependence to pull apart that expected value of a product. Once I've done that, well, Wi is almost surely less than W, because I'm to go from Wi to Wi, add on something that's either 0 or 1. And the reason that I want to do that is now I can get rid of any dependence on I in this sum. And so what I've got, just pulling the sum back into the expectation of my xi's. I've got the expected value of W, which is what I had on the bottom here, and the expected value of G of W plus 1. So just pulling that expected value over to the other side. If I divide through by the expected value of W, and what I've got is this thing here, which is telling me about my size bias version compared to my shifted version here. So when G was increasing, I've got exactly what I wanted. So, so what have I shown you? I've hopefully convinced you that total negative dependence is a sensible way of capturing this idea of negative dependence. So it's something that we might perhaps expect to see in applications, and I'll show you some applications where that happens later on. And I've convinced you that the monotonicity that we're assuming includes this class of sums of totally negatively dependent things. So hopefully that's convinced you that the assumption that we're making is a reasonable one, in that it captures some relatively intuitive notions of negative dependence and some things that we expect that we might see in applications. As Sergey points out in the chat, a very good reference for these kind of ordering ideas and applications to various systems and various stochastic systems, satisfying various kinds of monotonicity and ordering and things, is a book which is I know the later version in the which is co-written by Müller and Stein. There's an earlier version that was written just by Stein, but it's a very extremely good reference for these kind of things, which I don't think I mentioned elsewhere. So thank you, Sergey. Okay, so now that we've set up what I mean by the monotonicity, and I've told you what that means in terms of negative dependence, and I've perhaps convinced you that there may be some useful applications where this sort of thing is satisfied. Let's get back to the things I showed you before, which is the sort of the bound that we can get here, which again, the point is that this depends only on the first two moments of my W. Thanks to W, think of it again as the sum of dependent Bernoullis. All I need to know about, I don't need to know about the intricate covariance structure necessarily. All I need to know about is the first two moments of my W. And I can get under this negative dependence condition that my size bias version is smaller than my shifted version. I can get an explicit total variation bound that only depends on the first two moments of W. So the bound is nicer. The price that we pay is that we have to check that this monotonicity condition holds. So let me show you how we get that, and this will, I think, also show you that that the stochastic ordering is a sort of natural thing to assume here, in the sense that it makes it's clear where you want to use it in the proof. I've hopefully already convinced you that the stochastic ordering is a natural thing because it gives us things like the total negative dependence that we want. So if I want to bound this total variation distance, what do I need to look at? Well, I use my Stein ideas. I want to bound the difference between the expected value of f of my shifted version and f of my size bias version, where f is a solution of my Stein equation, which for total variation distance, I'm giving you bounded functions h. So let's do the simple thing and just write out what that difference in expectations is. So I've got the mass function of my shifted version of the mass function and my size bias version, I'll just rearrange that sum slightly by essentially a sort of discrete integration by parts formula, where I'm now writing that not in terms of f, but in terms of the increments of f, so that the steps of f, so the difference between f of j plus 1 and f of j. And if I use the sort of discrete integration by parts formula, if I want to write this, if I want to change this f in terms of into the increments, that will change this these masses into right tail probabilities. So just essentially playing around with a discrete integration by parts gets me right tail probabilities there. And then, well, what do I want to do? I want to take the absolute value of these things. So we'll do the completely obvious thing and use the triangle inequality to take absolute values inside this sum. I didn't mean to do that, but never mind. So we take absolute values inside this sum. I know how the steps of the increments of these f, of this function f, behave. They're at most, what is it, 1 minus e to the minus lambda divided by lambda. So they're at most of size 1 over lambda. So I can bound those by how big they are, which is fine. Oh yeah, that lambda appears because I'm missing a lambda here, but that's all right. I'm not missing it there. There shouldn't be a lambda there. These formulas are correct, but then we get an extra factor lambda that I just didn't bother writing down on the previous line because I don't need it. And then, so I've taken my triangle, I use my triangle inequality which pops me some absolute values there. And what I want to do essentially, if I want to make my bound as simple as possible, I want to throw away those absolute value signs, because then what I've got a sum of right tail probabilities, and I know how they work. That sums of right tail probabilities give me an expectation. So if I can throw away those absolute value signs, then everything's much easier, and I just end up looking at the difference between the expected value of w plus 1 and the expected value of the size bias version of w. And so what's the right definition to let me just throw away those the right assumptions, let me throw away those absolute value signs? It's precisely that, precisely a stochastic ordering between w plus 1 and w star, because that stochastic ordering was exactly by definition the setting where these right tail probabilities are always larger for one than the other. So it's exactly the right assumption to make to let me do the simplest, stupidest thing I can in my proof to give me the simplest, stupidest sort of bound, but it works. So let's do that. We'll use the monotonicity I'm assuming to throw away those absolute value signs. So I'm just left with the differences of expectations. So expectation of w we're assuming was lambda, the same parameter that I've picked for my Poisson distribution. As I said at some point last week, I think it's one fairly natural choice to choose the mean of my Poisson to have the same mean as the w that I'm approximating. It's not the only possible choice, and you just end up with some extra terms in the error bounds that don't really do anything very exciting for you. So we'll always assume that my Poisson has the same mean as w, but it's not necessary really. So I know that the mean of w is lambda. I can work out the mean of w star, because all I want to do is take the function g of x equals x there, and with that choice, if I take g of x equals x, then what's the expected value of w star? Well, it's just the expected value of x times g of x is just, so I get a w squared divided by the mean of w. Shift that slightly. So I just get that's how I end up with second moments. So that's where that second moment comes from. It comes from the expected value of my size bias version. Okay, so the proof of that kind of result is, I mean, it's really didn't require any intelligence, right? I mean, it's really not, there's nothing complicated. It's doing the most straightforward, simple thing. So really, the bound is essentially as good as you can possibly get. I think. So really, all that's kind of left is to find some useful applications where we can say where this monotonicity that we're assuming really does hold. So I've told you it holds under total negative dependence. What I need to show you, I guess, are some applications either where I can show you that total negative dependence holds, or that that monotonicity that we're assuming holds directly. I can use either definition to give you some either assumption to convince you that these things are useful. If I want to convince you that there's some kind of monotonicity, then what I at some point will need to do is actually explicitly write down some size biased random variables, actually construct these on the same probability space as the W that I started with, and show you that there's almost sure inequality between W plus 1 and the size biased version. So that's one way that I can convince you that this monotonicity holds, is by using the fact that stochastic ordering is the same as saying that I can construct these things on the same probability space with some almost sure inequality between them. If I want to do that, and I want to think about the example where I've got a sum of dependent Bernoullis, then I'm going to need to think about how to size bias a sum of dependent random variables. But we can do that, which is good. So there's a result whose proof I'm not going to give you, but it's actually not too terrible. That says if I want to size bias a sum of dependent Bernoulli random variables, so then what I'm going to do is I'm going to pick one of my Bernoullis. I'm going to pick one of my x's. I'm going to size bias that. I'm going to replace all the rest of my Bernoulli random variables by what I would get conditional on the thing that I've size biased. Okay. So I have to give you some more details before I've told you everything, but the idea is I've got this collection of Bernoulli random variables. I can size bias the sum by picking one of them, size biasing that, then conditioning all the rest on the thing that I've just size biased. So first of all, how do I size bias a Bernoulli? Well, size biasing a Bernoulli is particularly simple because one thing that we saw that the probability that my size bias version is equal to j in this nice discrete setting is just j times the probability x equals j divided by the mean. Well, if that random variable x is Bernoulli and only takes values 0 or 1, well, then that definition is going to tell me that a size biased version of that Bernoulli random variable is always going to be 1. Okay. So size biasing a Bernoulli random variable is particularly straightforward. I'm just replacing that Bernoulli random variable by 1. So that's where that 1 comes from, because I've size biased one of my Bernoullis. How am I choosing which one I want to size bias? I'm choosing independently of everything else with probability proportional to the mean. So I'm choosing, so each of these x's have mean, so xi has mean pi. I'm choosing to bias the ith of these x's with probability pi, essentially normalized by lambda, because those pi's don't, I'll turn them into a probability distribution. So I choose one weighted according to its mean. I size bias it by replacing it with 1, and then replace all the others by replace all my other xj's by xj conditional on seeing on the ith, the thing that I've chosen, being 1. So we saw in the when we were doing Gaussian approximation, we saw a very similar result for zero biasing there. We saw that we talked only about sums of independent things, but we saw that I could zero bias a sum by choosing one of my summands in a slightly different way then, and replacing that by its zero biased version. And there's this sort of size biasing analog, but in this case it's sort of slightly more straightforward to write down the dependent version as well. So in particular, if these W's were independent, then all I'm doing is picking one of them according to their mean. This conditioning doesn't do anything, so I'm just replacing the one that I picked according to its mean by 1. So somehow, and this is, you're sort of somehow, yeah, no, okay, no, let me not say that. I think I've just about, no, maybe I should leave the example till after the break, because probably it would be good to have 5 minutes before we think about the application. So what do I want to do after a break? I want to show you a couple of applications of these kind of ideas. I want to talk about how we can think about, not about negative dependence, but about positive dependence. I want to very, very quickly go through a couple of other settings where these kind of monotonicity conditions hold, and just show you that they crop up in other areas of probability as well, which will have very little to do with Stein's method. And then the last thing I want to do today, so in kind of slightly less than an hour's time, also doesn't really have anything to do with Stein's method, but is using size biasing in a different sort of setting to derive concentration inequalities. So I want to essentially, a lot of what I'm going to do for the last, say, half hour of today's session will be not directly related to Stein's method, but sort of building off the things that we'll have done for the first bit on Poisson approximation, which I think is fair. Well, I think it's fine. Just before the break, I'll just, as Sergey pointed out, that the Liggett who contributed an awful lot to applied probability, including this notion of ultralog concavity, passed away fairly recently, so just a few days ago. He worked an awful lot in an awful lot of areas of stochastic systems, dynamical systems, contributed an awful lot to various areas of applied probability. So that's probably a sensible point for a break. 10 minutes. So you meet again at 10 past. Sound reasonable?
Yep. Nice one.
Oh, sounds good. Thank you.
See you in 10 minutes.
See you all in 10 minutes.
I think we can start.
Yeah, if everyone's ready. Yeah, right. We have to. Okay, so I just want to show you a couple of applications after all that discussion of negative dependence things. So let me write down what our negative dependence condition was before I forget. So we had this negative dependence condition. Which said that my size bias version is smaller in a stochastic sense than the shifted version. So that's good. Okay, so here's one setting where that holds. So relatively simple sort of hypergeometric setting. So I've got some number of balls sitting in a bucket somewhere. Some of them are red, some of them are whatever other color I said, white. So we pick some of these ones, and I'm interested in counting how many red balls it is that I've picked. So we've got capital N balls in total. Little n of them are red, all of the rest of them are white. I'm choosing m of these things. So I've got three parameters here, sort of usual hypergeometric distribution with 3 parameters, which is known to be more or less, at least approximately, Poisson in some regimes. So some of these things get big in certain ways. If I want to write down the number of red balls that I choose when I pick m of these things uniformly at random, then a natural way to do that is to have an indicator random variable, a Bernoulli random variable, for each of my red balls, which is just going to be 1 if that ball happens to be chosen, and it's going to be 0 if that ball isn't chosen. So those are dependent, and it's sort of reasonably intuitive that they're going to be negatively dependent, in that if I tell you that I chose, let's suppose these red balls are labeled 1 up to n, right, just for the sake of this discussion. If I tell you that I've chosen red ball number 1, if I tell you that that ball definitely was chosen as one of the m balls that I've chosen, well, then in some sense there's less room in my sample for all of the other red balls. So the other red balls are sort of less likely to be chosen in a certain sense. And that's a very imprecise way of thinking about this, but we can make that intuition precise. We can show that we have this, that we satisfy this negative dependence condition, in that I can explicitly couple my my size bias version W star to the W that I started with. So I assume that I've picked some of these red balls. I've picked m of them out of my bucket, out of my urn. Then how do I construct the size biased version of that sum of the newly random variables? So all I do is I use the lemma that we just had before the break. So what do I have to do? I have to size bias one of them, and replace the others by what I'd have conditional on those being size biased. In this setting, it doesn't matter which one I pick, because in this setting, all of these n red balls look the same. So all of those indicators are exchangeable, so it doesn't matter which one I pick. I can think of pick one uniformly at random, and that might as well be called number 1, because it doesn't matter. There's no labels on them that mean anything in this problem. So we'll just assume that the one that I've picked is the one that I've labeled 1, just to make the sample, make the notation slightly easier. All I'm going to do, so to construct my size bias version, so I look at my sample. If this red ball that happens to be called number 1 is already there, then I'm not going to do anything at all. If it's not there, then I'll choose one of the m balls that I've got in my sample and replace it with the red ball that I've picked, labeled 1. This sort of distinguished red ball that I've happened to have chosen from these n things. It was either in my sample or it wasn't. If it already is, then leave it there and do nothing. If it's not there, then just choose one of the things that are there and replace it by this thing that wasn't there before. That's essentially the same as conditioning on the fact that that ball was in my sample to begin with. It's more or less what I'm doing. I'm conditioning on the fact that now this particular red ball that I've distinguished from all the rest is there. Since, well, in this first case, nothing's changed, that's all right. In the second case, what I've done is I've chosen something to get rid of. So there was for every other red ball that's living here, numbers 2 up to n, then there's some positive probability that it was there in my sample and I chose to get rid of it. So what does that mean? It means that in this construction, the chances of seeing any given red ball in my new sample is smaller than the chances of it being there in the first place, because there's some positive probability that I've got rid of it, which means these indicators the indicator that my red ball is now in my sample is almost surely smaller than the indicator that it was there to begin with. Because the only thing I can possibly have done is get rid of it. I've either left it alone or I've got rid of it. There's no other options. And so what the lemma above tells me that my size biased version looks like essentially the size bias indicator that this first one was there, plus the indicators that all the other n-1 red balls were there, conditional on the fact that I picked the first one. But I know that these indicators because of the fact that I might have got rid of any of the red balls when I was doing this, these indicators are almost surely less than the indicators without this conditioning, which is, well, there's a 1 plus something which is certainly smaller than, or less than or equal to W, because W has an x1 in as well. So my original W, that sum started from 1, now it starts from 2. So certainly this thing's almost surely smaller than W plus 1, which tells me that I've got, because I've constructed my size bias version and my shifted version on the same probability space, they're coupled, so that the size bias version is almost surely less than the shifted version, then that tells me the stochastic ordering holds. And so I get my negative dependence assumption in that case. All this is an explicit coupling that makes precise the idea that if I tell you that I've picked red ball number 1, then that means there's less space for the other n-1 of them in my sample. This is just a precise coupling that makes that intuition into a precise mathematical statement. So I know that my negative dependence condition holds here. I can calculate the mean and the variance of my hypergeometric, and that gives me an explicit upper bound, just plugging that mean and that variance into my result. Remember, those first 2 moments, all I needed to know to get an upper bound once I know that my monotonicity holds. And firstly, this gives you an explicit upper bound. I can calculate for any little m, big N, and m, any parameters that I want to plug in, and that holds for any of those values. It also gives me some sense in which, well, I can understand cases in which that upper bound goes to 0. So I can think about how, let's say, big N and little n and little m might depend on big N. Think of some ways that they might grow with that big N, and conditions under which that means that upper bound goes to 0 as n gets large. There are all sorts of other examples that we can treat similarly. Essentially, the book by Barbara Holson-Janssen is full of sort of variations on this theme and more or less sophisticated couplings. The hypergeometric example is not a particularly clever or sophisticated coupling, but there are lots of coupling arguments that look a lot like that, so sometimes require a bit more care, but we can use in applications and examples where these kind of negative dependence things hold. One more example. So again, balls and urns. So this time I'm distributing balls among these urns. So I've got n urns all lined up and buckets. I've got k balls that I'm throwing these k balls into, each one uniformly at random, into one of these n buckets, and I want to count the number of empty buckets after I've done this for all k balls. So again, I can write that as just a sum of indicators that bucket I is empty at the end of all this. Those indicators are dependent. You would expect them to be negatively dependent, because if I tell you that bucket number 1 is empty, well then somehow all those k balls have got to go somewhere, so the chances of the other buckets being empty is somehow smaller, because now I've told you that there's one empty bucket, there's only n-1 other things for these same k balls to go into, so somehow the other buckets have sort of got to be emptier on average in some sense. And we can use the same kind of coupling idea that we just had, and I'll leave that to you to think about, to get an explicit upper, to tell me that my negative dependence assumption holds. And again, once I've got the first 2 moments, that lets me write down an explicit upper bound. Okay, are there any questions on any of this sort of negative dependence? Any of these negative dependence things that we've been talking about? They don't necessarily have to.
Everything is clear, as always. You're very good.
If anyone has any questions, then let me know. I'm happy to answer questions.
I mean, may I just repeat everything just for a few seconds? Yeah, that we have this problem with urn, and we like, instead of really probabilistic, not like analytically constructed size bias distribution, we constructed it in some way probabilistic way. We say that this one will be this one and blah 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 blah, and here is a new random variable that is exactly size biased of the initial one, and then we just construct a size biased random variable w using the lemma, and that's all. Yeah, and then we just used it. Okay, so
yeah, exactly. Thanks. Okay, so that's negative dependence, and a sort of natural follow-on from that is, well, is there some notion of positive dependence that we can write down in this sort of setting? And the answer is yes. And what we do, it's one of the sort of annoying features of this is that I can't just take that stochastic inequality that I had and reverse it. Somehow what I want to do is I want to write down positive dependence just by saying that my size bias version is stochastically larger than my shifted version. Okay, somehow that's the definition you want to write down, and it doesn't work. It doesn't work because that, for any random variable with a finite support, that can't possibly hold. So if I think about a random variable like a sum of n indicators, which is supported on the non-negative numbers up to n, then the maximum possible value of w star is going to be n, because my size bias thing can't take values bigger than the thing I started with. The w star is almost surely going to be at most n. Is almost surely at most n. W plus 1, annoyingly, can be as big as n plus 1, which means that, so this w plus 1 has got some mass strictly to the right of n, which w star doesn't have, and so that stochastic ordering can never hold. It can hold if my support's infinite, right? That's fine, but the problems we're interested in don't usually have infinite support. We're in general interested in sums of n dependent Bernoullis. So unfortunately, we can't just write down that write on the same inequality with a reverse sign. We have to do something a little bit different. And it turns out that, so thinking still about the case where we've got a sum of dependent Bernoullis, what I want to do is write down instead this thing. So my positive dependence condition is going to look like that, which is very similar to what we had before, in that, so my w star is this time greater or equal to w plus 1, take away something. The something that I'm going to take away is one of my x's chosen independently of everything else with probability proportional to its mean. So the same definition we were using when we were size biasing. I'm choosing one of my x's independently of everything else going on, and I'm choosing xi with probability proportional to the mean of that random variable.
So now it's not like a general definition. It's only for the sum of Bernoulli random variables.
Yeah, exactly. So I don't know how to write down a general thing like this. I mean, as you say, before we wrote down something that works for any random variable w, and applied it in the case where we had a sum of Bernoullis. Now we're really restricting our attention only to sums of Bernoulli random variables, and I don't know how to get around that.
Okay, thanks. No worries.
So if I do this, okay, so we've fixed the problem of the support, because now this thing can't be n plus 1, because if all of my x's were 1, then, well, I've got a plus 1 and a minus 1, so that's okay. And it turns out we can do something similar that we had before, in that I get an upper bound, which is more or less depends on only on the first two moments, but some extra term that we get because of this annoying x that I've had to choose. That term is just twice the sum of my pj squareds. So the pj's with a mean that was the mean of xj. So we can. I'm not going to show you the proof, but you can prove it in essentially exactly the same way as we did for the negative dependence case. Let me go back up to that proof quickly. Sorry. So exactly the same proof as we have for the negative dependence case. We're going to start in exactly the same way. Only if I want to get rid of absolute value signs, I can't do that directly. I have to sort of introduce this thing as well. So I'm going to. If within these absolute value signs I add and subtract the right tail of this thing, then I can use the triangle inequality to break that into two terms. One of those terms I can get rid of the absolute value signs by using this assumption, and the other one I can get rid of them because I've taken away something that's non-negative. I'll leave you to fill in the details, but the proof is not too terrible. From one of those terms we get what we had before, but with an extra sum of our pi squared, and the other term gives me the other pi squared term that I need. But it's not awful. And this is, in some sense, it's an assumption which works well in practice, in that you can do sort of analogues of this thing that we had to do with total negative dependence. If you sort of define total positive dependence in an analogous sort of way, then things work. So this does seem to capture ideas of positive dependence. And just to show you one example where this thing works. So if I want to count the triangles in an Erdős-Renyi graph. So Erdős-Renyi graph model. So I've got n vertices. Any pair of these things are connected by an edge with probability p, independent of everything else going on. So for each pair of vertices, I toss a coin, and if it's heads, which happens with probability p, I draw an edge between those two things. If it's tails, which happens with probability 1 minus p, then I don't. I can think about counting the number of triangles in that graph by, well, we've got an index set where I'm thinking about all possible triples of vertices. A triangle is just a set of 3 vertices where every pair of which are connected by an edge. So triangle is exactly what I want. Right? I've got 3 vertices. I've got an edge between these two, an edge between these two, and an edge between these two to make a triangle. So for every possible triple of vertices, every possible set of 3 vertices, I can have an indicator that tells me that all 3 of those edges are present. So if gamma is my set of all of my sets of 3 vertices, I just have an indicator for each of those sets of 3 that tells me that all 3 of those edges are present. Then I can construct my size bias version by just taking one of these 3 things. Let's call it alpha. Okay, we'll just fix one of these things. Again, everything here is exchangeable, so it doesn't matter which one I've chosen. They all look the same. The labeling is completely arbitrary. There's no fixed labeling of my vertices 1 up to n that matters. I can call them whatever I want, so I might as well call the one that I've chosen 1, 2, 3. Then I can. So what do I want to do? How do I construct my size bias version? I add in any edges that are missing from that would make this triangle. So if there was one, if that's 1, 2, and 3, if I only had that edge, then I'm going to add in a couple more edges to make that triangle. So I might add in that one and that one to finish off that triangle, so that I'm conditioning on that triangle being there, just conditioning on all 3 of those edges being present. But once I do that, I'm sort of intuitively in a positive dependence setting, because adding edges to my graph might make more triangles as well. I can't possibly get rid of any triangles that are already there, but I might add more of them. So all I can possibly do is make all of my other x's bigger, because I I might turn those from a 0 into a 1 by completing some other triangles as well. Like if I already had, here's vertex 4, if that was already connected to 1 and 3, then by adding in that blue edge there, I've made another triangle. There's a triangle that wasn't there if I just had the black edges, but once I draw that blue edge as well, then I've got an extra triangle. So I can use that to essentially check in the same kind of way that I had before, that I now have my stochastic ordering I need for my positive dependence, which tells me that this positive dependence assumption holds. Everything's sort of, well, the means and my sort of PI terms are easy to calculate. So what's the probability that I have a triangle? All three of those edges are present. Well, each edge is present with probability p, independently of everything else. So the probability of getting all three edges is p cubed. There are n choose 3 sets of these three edges. So my average number of edges is just n choose 3 times p cubed. I can calculate the variance and plug all those into an upper bound, which tells me, for example, it gives me, well, again, as with other examples we've looked at, it gives me an explicit upper bound that I can use for any values of n and p, but it also tells me about regimes in which I'll have Poisson convergence. So when will I get convergence and distribution of this number of triangles to a Poisson? Well, if I'll get that exactly when, I'll get that if that error bound is going to 0. So for example, if I take, let's see, p to look like constant divided by n and let n get large, then what I've got here will end up looking like a sort of 1 constant over n times term, which will go to 0, and that's a constant over n cubed, which will go to 0 as well. So I can check, for example, if p looks like the constant, like c over n for some constant c, then that upper bound is going to go to 0. Okay, I've got 25 minutes or so left, and what I'm intending to spend that time doing, sort of like I said, was show you spend at least 20 minutes showing you some things that aren't really Stein's method, but somehow touch on to things that we've talked about today in a way that I find interesting and sort of close enough to what's going on that I think it's sort of that they're worth mentioning. So there's a couple of places that I want to show you where these kind of monotonicity assumptions, and actually I'm going to think only about the negative dependence case because it's easier, where these kind of monotonicity assumptions are also useful. What we've seen so far is that they're useful in a sort of comparison between W and a Poisson random variable in a certain sense, in a sort of total variation of Wasserstein distance sense. I want to show you a couple of other senses in which we can, or other ways in which we can compare W to a Poisson, and in which these monotonicity assumptions, this negative dependence assumption, is also useful in terms of getting sort of explicit bounds or comparison between these sort of random variables W and a Poisson random variable. So one way I can do that is, or one way in which I can sort of think about this, so is in terms of this sort of Poincare constants and all sort of inverse spectral gap constants telling me about spectrum for sort of Markov operators and things and gaps between eigenvalues. So you can essentially the constant that you can get in a Poincare inequality for W, that's more or less comparing how big the expected value of g of W squared is compared to the expected value of the increments of g of W squared. The increments of g of W squared, that is. But just for functions for which that's defined and for which have expectation 0, why not? So that's sort of one thing you can, so just by choosing g to be a nice linear function, then that Poincare constant is always at least as big as the variance, and we know that that a Poisson random variable is characterized by having its Poincare constant equal to its mean, which is also the same as its variance. So this thing's at least as big as the variance. That's relatively easy to show. Choose G to be linear, and then it's equal to that variance if and only if we happen to be Poisson. And we can actually show. Let me skip ahead a little bit. I'm going to go quickly because this is sort of away from the main point of what we're doing, and I want to fit in a few things since this is my last week, and I want to sort of finish off with a few comments on things. I'm definitely not going to fill in details, but whoops, I've lost the. Sorry, I've lost what I want to say. Oh, there we go. Okay, so I'm Poisson if and only if this Poincare constant is equal to my mean, and one thing I can show is that if I satisfy my negative dependence condition, then my Poincare constant is bounded by my mean. So upper bounds on this Poincare constant are generally tricky-ish to get. I mean, they're certainly harder than lower bounds. The variance gives a very reasonable lower bound, but getting upper bounds is sort of relatively harder. But under this monotonicity condition, we can get an upper bound without too much work. And we can also, and this gives us a sort of explicit comparison between W and a Poisson, because I know that equality holds here if my W happened to be Poisson, because I know in that case my Poincare constant is lambda. So where do I use my monotonicity here? So I end up writing down, so one of the terms in my Poincare constant was this expectation of G of W squared. The other thing was to do with the expectation of the square of the increments of my G. So I write down a representation for that in terms of this kernel function. So there's some sort of kernel function that Poisson defined at some point that lets me write this. I'm going quickly. I don't expect you to follow everything I'm saying, but I just want to show you where this monotonicity appears. We get some size biasing. I've got an I times the probability W equals I, so that's a size bias type thing. And so when I sort of chug through, what I can get eventually is, let's take Z equals 1 for the sake of what we're doing. Z is 1. I can write this down as the expectation of an increasing function of W plus 1. So this kernel function is increasing in its first argument, and in the case we're interested in, this Z is just 1. Oh, that's horrible notation. Sorry, I've used Z for a Poisson everywhere else. I copied and pasted from somewhere different. Okay, I'll change that notation. Z is just 1. Sorry, I broke my own convention of only using Z for a Poisson. That's a 1. Sorry.
No problem.
Yeah, anyway, sorry, where was I? Yeah, so an increasing function of W size bias and W, which I can then use my monotonicity to replace that by a W plus 1, which then lets this whole thing simplify just to give me exactly what I want, to give me the mass function of W. So if I use my monotonicity to replace that by W plus 1, and then this whole thing just simplifies to a mass function and gives me a nice simple bound. So that's another sense in which I can compare W to a Poisson using some monotonicity. I will fix the notation to be more consistent with the rest of the lecture notes before I send you all out a copy. I think at some point I promised you a copy with typos that we've noticed during the lectures fixed. I'll do that. I'll fix that notation as well and email it out to everyone, hopefully today or tomorrow.
Okay, but now you introduced this Poincare constant.
Yeah.
And you show us some property of this constant, but why we need this? Just to understand, we have like random variable Poisson distributed or not?
Yes. So that's one way we can use it. We can use it to write down sort of explicit Poincare inequalities for these random variables, which can be useful in sort of variance bounding inequalities that can be useful in sort of various kinds of problems. So
okay.
we're not using them for anything else. I just want to illustrate the point from my point of view is to show you a case where these monotonicity conditions can help as well. Another setting where they help is in getting entropy bounds. Actually, it follows as a corollary of something else, but I'm saying something else about that. So I can show you. I can compare the entropy of this random variable W to the entropy of a Poisson random variable. Oh, sorry. I can show you that the entropy of W is less than or equal to the entropy of a Poisson. So it gives me another way of sort of comparing W to Poisson in the setting where I have this this negative dependence. The sort of nice feature that we can exploit here is if I draw or construct a sort of path of random variables that has my W at one end and my Poisson at the other. So at the moment I've been thinking just about these two random variables. I've been comparing W to a Poisson. But let's kind of join them up with a sort of path with some parameter that runs from alpha equals 0 at one end to alpha equals 1 at the other, by defining a random variable which looks like this. Okay? So for any number alpha between 0 and 1, I'm going to thin my W by parameter alpha. So what does that mean? It means I'm going to replace. It means I'm going to take a sum of W independent Bernoulli random variables, each with parameter alpha. So essentially, for each thing in my W, I'm throwing away each one that appears there with probability 1 minus alpha. I'm keeping it with probability alpha. So I'm thinning this W, and then I'm making myself back up to having a mean lambda by adding on an independent Poisson random variable with mean 1 minus alpha times lambda. So I'm throwing away some proportion 1 minus alpha of my W, that W has mean lambda. I'm making that back up again by adding on a Poisson thing. So when alpha is 1, then I'm not throwing away any of my W, and I'm adding on a Poisson with mean 0. Think of it just as a mass at 0. So when alpha equals 1, I've got W. When alpha equals 0, I'm throwing away all of my W, and I've got a Poisson with mean lambda. So from alpha equals 0 to I've got a Poisson thing. When alpha equals 1, I've got W, and I can define a random variable for any value of alpha between 0 and 1. So I've got this sort of family of random variables, and so the nice thing that holds, and the thing that lets us get a handle on sort of entropy bounds, so actually sort of is the fact that if the W I started off with satisfies its negative dependence condition, then so do all of these random variables along this path. For any alpha that I want to start with, that they all have the same monotonicity. That's just a whole, and that's one or two applications of how to size bias a sum, and because my W alpha is just a sum of two things, the thinned part of W and a Poisson, and so I need to know how to size bias those sums, and I use various closure properties of the stochastic ordering to show this. So once I've drawn this path, I know that all of my random variables along that path satisfy this monotonicity condition, and I can use that to show that as I go along that path from alpha equals 0, where I was Poisson, to alpha equals 1, where I was where I had W, that my entropy is decreasing, and what's that? Concave. So in particular, that tells me that because my entropy is a decreasing function along that path from alpha equals 0 to 1, that my Poisson has sort of maximum entropy of all those random variables, and so the entropy of my W can be bounded by the entropy of my Poisson with mean lambda, for which there aren't nice expressions, but there are quite reasonable upper bounds. So it's sort of another sense in which I can compare W to a Poisson using this kind of monotonicity assumptions. That was sort of another quick 5 minutes that was a bit away from the main topic that I was talking about today, but sort of other places in which this kind of negative dependence condition can appear. Okay, the last thing I want to say, just for 5 or 10 minutes, just to finish off this section on Poisson approximation. So one other use of size bias couplings is improving concentration inequalities. So if I want to put bounds on tail probabilities for my random variable W, or at least some normalized version of that. So I'm getting away. I'm not assuming I'm not assuming this sort of negative dependence condition or positive dependence or anything here. This is the only thing I'm going to say today that isn't really related to that. But one thing that we've already seen when we talked about Gaussian approximation is that bounded couplings can be useful. So we saw some examples where we could exploit boundedness of couplings. So if I want to assume that my size bias coupling is bounded, in the sense that I can construct my size bias version of W in such a way that the difference between the size bias version of W is always non-negative and is at most is almost surely less than C for some constant C. I can use that to get some concentration inequality for the W that I started with, some bound on the tail probabilities. So I guess one thing to say is, so this size bias version W star is always, it is stochastically bigger than W. Okay, so I can show that when I make this transformation that my W star is stochastically larger than W. But there's certainly there's always a size bias coupling such that difference is non-negative, but that doesn't guarantee that it's bounded. So the boundedness is really the sort of extra assumption that we're making here, and that I can always construct these things to be non-negative, this difference to be non-negative, but I can't necessarily construct it to be bounded. So I just want to show you this, not because it's related to the monotonicity we've been thinking about, but because I think it follows on quite nicely from the things we were talking about a couple of weeks ago when we were looking at using bounded couplings, and in particular some bounded size bias couplings for approximation, for Gaussian approximation. Somehow this fits in most naturally in a Poisson setting, because we're thinking about non-negative integer valued random variables. So mean lambda, variance sigma squared. So I've got some exponential bounds for tail probabilities, which I can. So how do we prove these? So I've got sort of 5 minutes just to give you a sketch of the proof. The details of the proof are all here. And if you want to look up it's a paper by Goldstein and Ghosh that has details in, and they've done some follow-on work with a couple of other applications of this as well. But I can use moment generating functions just to prove this, essentially by exploiting the fact that I can write the derivative of my moment generating function. So the moment generating function just said, what did I give it? I probably don't write that in definition somewhere. So the expectation of e to the power theta times W, if I differentiate that with respect to its argument theta, this brings down a W, which then looks an awful lot like what I've got is size biasing. I've got a sort of WG of W type of term. So that's exactly the mean of W times the moment generating function of my size bias version, and I can go on to use some monotonicity between the boundedness between my size bias coupling and my original W to be able to bound this thing, because I'm going to get that by just using some inequality to do with my exponentials, I can write down write down an inequality of the difference between what's going to end up being essentially the moment generating, or the expectation of this thing here. Okay? It's trying to say it in words is longer than it should be, but this quantity here, the difference between the e to the power theta of my size bias version minus e to the power theta of my original w. I can use that inequality to bound that in terms of the sum of those two exponential terms. Use that inequality to use the inequality in the boundedness, so to bound that difference in terms of that constant c, in terms of the moment generating function of my w's, and then use that in turn to give me a lower bound for this moment generating function of my size bias version, which, as I say, I can interpret in terms of. So I'm using the boundedness to write down this lower bound. I'm using the fact that I have this constant c that is an almost sure bound for the difference between w and w star. Use that to bound this derivative of the moment generating function I started with. Once we normalize the problem, that turns into a lower bound on the derivative just for the normalized random variable. So just to subtract the mean divided by standard deviation in the usual sort of way. I use that lower bound to write down lower bound on my an upper bound on my m of theta via a lower bound on minus log of that moment generating function. Just plug in that upper bound of what I get there, so I can get an upper bound on my capital M of theta just by taking exponentials. So I get this upper bound, and then usual sort of Hofting approach to use that upper bound on a moment generating function to give me a concentration inequality. So for any value, for any theta that I want, I think I'm assuming theta is negative somewhere here. I can't remember where I need this, but somewhere we'll need theta to be negative, I guess, just to make sure that we don't mess up the directions of my inequalities along the way. But for any negative theta, so that inequality turns around, I can write down this tail probability in terms of my moment generating function times this e to the power theta t. I had an upper bound for this moment generating function. I then just want to choose the value of my parameter theta to make this as small as possible. So I just choose theta to look like that, to give me the upper bound that I want. It's sort of quite a nice application, I think, of size bias couplings, in that what I wanted is a bound on the derivative of my moment generating function, but I can get that by using by writing the derivative of my moment generating function in terms of the moment generating function of my size biased version, and then it's sort of that an upper bound then follows from this boundedness. The boundedness gives me a sort of explicit probabilistic way of thinking about situations in which this holds. So the size bias couplings are things that we can construct explicitly to show this boundedness. So somehow derivatives of moment generating functions are very nice analytic tools, but somehow it's harder, it can be harder, I think, to get a handle on them probabilistically, whereas this sort of thinking about size bias couplings gives me a nice probabilistic interpretation of what I'm doing. Just to finish off in the last couple of minutes, you can show, for example, that if I have a sum of independent Bernoulli random variables, well, we know how to size bias that, because we've actually seen the more general result of size biasing a sum of dependent Bernoullis. So I know how to size bias a sum of independent Bernoullis, and that will let me see that I can apply this result with a constant c equals 1. Slightly more interesting example. So let's think about a sequence of coin tosses where each of my coins comes up heads with probability p, and what I want to do is count the number of runs of m consecutive heads in a sequence of coin tosses. So think of heads as corresponding to a 1 with these Bernoulli random variables, tails as a 0. So I want to count how many. Well, I can tell you whether or not there was a run of m heads starting at a particular point by just counting, by just multiplying together all those things, all those coin tosses. If they were all heads, and that's 1 times 1 times 1 times 1 and so on, which gives me a 1. If one of them was tails, then I get a 0 somewhere, which means that product is a 0. So all I'm doing is counting the number of, if I've got, yeah, I'm counting the number of heads by just letting heads be the same as these Bernoulli random variables being 1, multiplying together the corresponding set of Bernoulli random variables. Just for the sake of having a convention, I'm sort of assuming these things are sort of appearing on a circle, so that at some point when I get big enough, this thing drops off the end of my sequence of n coin tosses. So I'm just going to go back to the beginning, so that so I'm taking a convention that all my indices are treated modulo n. So essentially, I'm looking at these coin tosses rather than on a straight line with a beginning and an end. I'm sort of thinking about them on a circle, so that I'm just kind of looking at points around that circle. So I can calculate the mean and the variance. The mean is not too hard. The variance takes a little bit more thought. So for the mean, I've got n possible points at which a run of heads could start. That run of heads has probability p to the power m, because each head has probability p, and I need m of them. They're all independent. These are sort of locally dependent random variables in the sense that if my locations are too far apart, then they're independent. If the set of times I'm looking at are disjoint, then there's no coin tosses in common, so those things are independent. And I can use a similar sort of size biasing argument. This time thinking about size biasing as sum of dependent random variables to show that I can take the boundedness here of my size bias coupling to be dependent on this m that essentially controls how big a time window I'm looking at, and so I can get some concentration inequality there. So there are definitely some details to fill in there, but I'm not going to do that because I'm already out of time, but there's an example you can sort of work through if you want to. All this Poisson stuff, just finding we could generalize to compound Poisson approximation if we wanted to, where I'm thinking about a sort of Poisson number of clumps of events. There's some comments there about that. And I could also generalize everything to sort of Poisson process approximations, which I'm sort of not going to do. And now the role of size biasing is played essentially by palm distributions. So those of you who are familiar with those, that's what they're doing in this setting. But let me stop there because I'm already out of time, and I want to give you a chance in case there's any questions that before I go away.
Thanks. Anyone have any questions? I have one about the concentration inequality. It looks like it's very close to Bernstein inequality, as I understand, or not?
Yes, yeah, it is.
In Bernstein inequality, you need to have a bounded random variable, as I remember, and here you can have like not bounded even. But
yeah,
they're like positive, they're bounded from one side.
Yeah. So, but yeah, you don't need the W doesn't need an almost short upper bound as long as the difference between the W and the size bias version is bounded. Yeah.
Mm-hmm. So it's in some sense quite different.
Yes, yeah, in that sense, yeah. But the upper bound that we get is a similar sort of flavor to all these other kinds of concentration inequalities that you get. Yeah.
So, any more questions?
I still have this question about positive dependence. I mean, it still kind of breaks me that the Poisson distribution kind of means that size bias transformation is almost, or in distribution, like W plus 1.
Yeah.
But when we talk about positive dependence, then saying that W star is bigger or equal W plus 1 doesn't make sense. That's just kind of, I don't know. Is there any intuition, or is it like, is this the definition of like W star, what it actually means? I don't know. Can you comment on this?
So
It
sorry,
it was a question of support.
Yeah.
For Poisson distribution is
So this gives you at least a reason why the more natural thing to do, just reversing that inequality, doesn't work. Aside from the sort of point about the fact that there's mass here at n+1 and there isn't mass here at n+1, I don't have any other good reasons. If you sort of read, if you sort of dig into various papers about sort of positive and negative dependence, then they do end up working more differently than you would expect, in the sense that there are certain techniques which work more easily in a negative dependence setting, but which don't carry over to a positive dependence setting, which is sort of where we are now. And there are other papers which sort of argue that negative dependence is harder for various reasons, and it's sort of the sort of nice things that work in a positive dependence setting don't carry over to negative dependence, and somehow the point that you're making about sort of difference here carries over much more generally, and I don't fully understand it. I don't think.
Okay, thank you.
I can see analytically why things don't work, but I'm not sure I don't think I appreciate as well as I would like the reasons why there seem to be such differences between positive and negative dependence in sort of universally.
Okay, thank you.
Yeah, thank you, Fraser, for this small course of lectures. We initially think that it will be a small one, but as I see, you already finished 40 pages and you have only 15 less. So I have one more question. What you will read for us at autumn, or maybe like next time when we will see each other offline?
So there's still some material left. So there's a couple of other sections in this in the lecture notes, and I haven't thought about what else to fill the time with yet. If you have requests, then please feel free to pass them on. I don't guarantee to do exactly what you want, because I still have I retain control over what's in the lecture notes, and I'll decide what's interesting to me to a certain extent. But
Okay.
But I'm certainly happy to take requests if people have some of the topics that they'd like me to cover in a sort of second half.
Yeah, we can do it.
We did go relatively quickly through a lot of this stuff. I mean, certainly I would have spent more time on some pieces if we'd had more lectures, but it felt like covering Gaussian and Poisson is sort of in some sense the minimum that you need for an introduction to these sorts of ideas. And it felt like the natural point to stop, because it's sort of, we've covered a lot of the classical material, I think.
So I think everybody can advance. Switch on your microphones, yeah.
Thank you, everybody, for being here with us. Yeah.
Yeah, thank you very much for participation, and it's been good to meet you all in some sense. And hopefully have a chance to meet you all in person later on.
Yeah, it will be very interesting for students to meet you. I mean, I'm sure it's something like usually you first see each other offline and then only online, but it's something very different. Yeah.
Yes, yeah. This is the way of the world at the moment.
Okay, see you next time.
Thank you very much. See you all soon, I hope. Thank you.
Yeah.
Thank you.
Bye-bye.
Cheerio. Bye.
Bye.
Thank you.